In this video, I want to make some considerations on the Zeta Function Regularization and the divergent series. Let's start from the following series. So we're going to start from, actually this is just a summation, a finite summation at first, with the index n going from 1 to capital N. So you might understand that we will also let capital N go to infinity later, but for now this is just an integer, and you can think of this as a large integer. And then here we have n to the power k, where k is another integer, so this will be an integer, and later we'll think of this both as a negative integer and also as a positive integer, but for now this is a positive integer, so k greater than 0 for now. And this is equal to, we can also rewrite this as, now let me write it down, then I will explain more. So we can take the partial derivative with respect to a parameter that I still have to define, alpha, k times, then we take the derivative of the following summation from 1 to capital N exponential to the minus n alpha, and then we also have to multiply this by minus 1 to the power k that I can put in here. So let me cancel this equal sign. I will put it here, and then we have minus 1 to the power k. So if you check here, when we take the derivative with respect to alpha n times, we are going to act on this exponential, so this will give us minus n to the power k. So this is equal to minus 1 to the power k, n to the power k, which is going to, we have to put n to the power k here in front of the exponential, and then minus 1 to the power k, when we multiply it by minus 1 to the power k, we're going to get a factor of 1. So if we really want these two to be equal, we have to calculate the limit as alpha goes to 0, and we will think of this as 0 plus, in the sense that we think of alpha as a positive quantity, and therefore we can say that e to the minus n alpha is between 1 and 0. Okay, so we have to take this limit because otherwise we cannot put the equal sign. So we can put the equal sign only when we let alpha go to 0 after we make this calculation, after we do this calculation, and therefore this exponential will go to 1 after we let alpha go to 0. So when alpha goes to 0, this exponential is actually equal to 1. In general, if alpha is greater than 0, e to the minus n alpha will be between 0 and 1. Now let's focus on this summation here. So if we focus on that, we have summation over n from 1 to capital N e to the minus n alpha. Now this can also be written like this, summation over n from 1 to capital N e to the minus alpha, which is raised to the power n, and we can call e to the minus alpha just x for the sake of convenience. So this summation would imply x plus x squared plus dot 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 plus x to the power n, right? So if we multiply this by 1 minus x and we divide by, of course, the same thing, this is also equal to, so we can rewrite this, so if we multiply out these terms, you can easily understand that this will be equal to x minus x to the power n plus 1, and we divide by 1 minus x, right? Because when we multiply out these terms, this first one multiplied by 1 will not be cancelled if you think about it. But if we multiply x squared, with 1, so we have x squared, but this will get cancelled by x times minus x, because that's minus x squared. So there are some terms in between that are going to get cancelled. And the final term that will not be cancelled is minus x to the power n plus 1. So when x to the power n is multiplied by minus x, we are going to get this term that's not going to get cancelled. Now this can also be rewritten for the sake of convenience as 1 minus x to the power n plus 1 divided by 1 minus x minus 1, like this. Therefore, if you remember the definition for x, here we have 1 minus e to the minus alpha to the n plus 1. So we can multiply the argument here alpha by n plus 1 for the properties of exponentials, and then we divide by 1 minus e to the minus alpha, and we subtract 1 like this. Now let's focus on this denominator. In particular, we can rewrite 1 over 1 minus e to the minus alpha. So, this quantity multiplies this numerator. So I'm going to make some considerations only on the denominator, so in particular on this term, which appears in that expression. This can be written as 1 over 1 minus, and then I'm going to expand this exponential, so I have 1 minus alpha plus alpha squared over 2 factorial minus alpha cubed over 3 factorial plus dot dot dot. So I can rewrite this term like this, 1 over, so this 1 will cancel this 1, and I will be left with alpha, and if you check, I can also factor out alpha, so I have, in particular, I have 1 minus alpha over 2 factorial plus alpha squared over 3 factorial minus alpha cubed over 4 factorial, and then you understand the pattern, right? So I can factor out 1 over alpha here, so I have 1 over alpha, which multiplies 1 divided by 1 minus alpha over 2 factorial minus alpha squared over 3 factorial plus alpha cubed over 4 factorial plus dot dot dot. So you understand the pattern. Now, if we call this term inside this parenthesis just y, here we have, if we consider this fraction, here we have 1 over 1 minus y. So this can also be written as 1 plus y squared plus y cubed, and you understand the pattern, right? So in particular, this will be the summation over k from 0 to infinity, y to the k, and this holds if mod y is less than 1, right? So we can rewrite this like this. So we have 1 over alpha. Remember that at the end of the day, we will have to let alpha go to 0. So we can think of this quantity inside this parenthesis as being small, because we are in the vicinity of alpha equal to 0. First, remember that we have to take the derivatives, and then we let alpha go to 0 from the right. So that's a 0 plus, if you think about it. Anyway, here I have a bracket, so I have 1 plus y, so I'm using this formula here, but y is just alpha over 2 factorial minus alpha squared over 3 factorial plus dot dot dot, and then you have plus alpha over 2 factorial minus alpha squared over 3 factorial plus dot 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 squared, and you understand the pattern. So if I go back to my formula here, I can rewrite it. So I'm going to rewrite exactly this, where is it? Sorry. This result. Remember that we have expanded this denominator, in particular this term. So I can rewrite that formula in the following manner. So I have a summation over n from 1 to capital N e to the minus n alpha, and then I have 1 minus e to the minus alpha n plus 1. This multiplies that denominator that we have expanded like this. So we have 1 over alpha, 1 plus alpha over 2 factorial minus alpha squared over 3 factorial plus dot dot dot, and then you have plus, we have alpha over 2 factorial minus alpha squared over 3 factorial plus dot 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 squared plus dot dot dot, And then finally, remember that we also have to subtract 1 from here. Now, at this point, we want to calculate the following summation. Suppose that we want to calculate this n from 1 to capital N of n, right? And remember where we started. So we started here with this expression. So from here, if we set k equal to 1, we can use this formula. And also remember that we have done some work for this summation, so we also have to remember that one. So this is equal to minus the derivative with respect to alpha only one time, because k is equal to 1. Remember that we have to set alpha, we have to take a limit as alpha goes to 0. So this summation is the limit. So here we have already taken the limit for alpha going to 0. Okay, so I will write it like this. And then here we have to put these quantities. We have exactly this expression here. Now, since alpha, we will have to take alpha, we have to take the limit as alpha goes to 0, and here we have a capital N. We have not said anything about capital N. In principle, this could be something very large, but we have to think that this is still something finite for now. And when we let alpha go to 0, we can expand, if you think about it, this in particular this quantity. So let's consider this quantity. If we expand it, in particular the numerator here, we can expand it. So we have 1 minus, and then when we expand the exponential, we have another 1, right? This will cancel this 1 here, so I can get rid of that 1. Remember that we have this minus, then we have alpha times n plus 1, and in principle we could have other higher order terms. Let's take also the higher order, so the second order, minus alpha squared over 2 factorial, which is just 2. And then we also have n plus 1 squared here, and we divide by this alpha here. So we will realize soon that we also need this second order quantity. And in principle we can have other higher order terms here, but they will not be necessary. So we have this. Remember that this multiplies all of this, actually only this, and then we have this minus 1, but since we are taking the derivative with respect to alpha, this minus 1 can be neglected, because the derivative with respect to alpha of a constant is just a 0. So we can avoid writing down this minus 1. And then what do we have here? We have just 1 plus alpha over 2 factorial minus alpha squared over 3 factorial plus dot dot dot. And then we also have this. So we have plus these other terms. So we have alpha over 2 factorial minus alpha squared over 3 factorial plus dot 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 squared plus dot dot dot, like this. So we can close this bracket. And in principle here we have to do a calculation, right? So we can simplify first this alpha with the alpha and alpha squared. So we can simplify this a little bit. So let me cancel this alpha. I cancel that alpha. I can cancel that with alpha, and here we can remove this alpha. So I have something like this, right? And then remember that we have to take the derivative with respect to alpha, and at the end of the day we have to let alpha go to 0. So there are some terms that will go to 0 when we let alpha go to 0. So this will be higher order terms. For example, if I consider alpha squared multiplied by this constant, this will not give me a contribution, because when I take the derivative, a term that is proportional to alpha squared, when I take the derivative with respect to alpha, this will give me a term proportional to alpha. So when I let alpha go to 0, this will give me 0. So that's not something that's going to appear in my final formula. I only have to be interested in terms that are linear. in alpha. Because when I take the derivative with respect to a term that is linear in alpha, well, I'm going to get the result, because if I let alpha go to 0, that constant term, does not go to 0, right? So the only terms that I'm really interested in when I take this derivative are n plus 1 multiplied by alpha over 2 factorial, right? Because the only linear term in alpha coming from these square brackets here is this one, alpha over 2, because this one here actually does not contain terms that are proportional to alpha. Since we are raising this to the second power, this alpha will become alpha squared. So this will be higher order terms in this case, right? It would not be the case if we had, for example, to consider a second derivative here, which would lead us to summation of n squared, right? So this is just the intuition. So here we have minus alpha over 2 n plus 1 squared, which is this term, but then we also have plus n plus 1 from here multiplied by alpha over 2 factorial, which is just 2. So the result, all in all, is just when we take this derivative and we also consider this minus sign, is n plus 1 squared minus n plus 1 over 2, which is n plus 1 times n divided by 2. So this is a well-known result. It is the summation of n, and this gives us the following result. So this is nothing unexpected, and you can see that when n gets larger and larger, this summation here is divergent, and there is no hint as to the zeta function from here. So if you let n go to infinity, you see that, this will give us a divergence, and it tells us nothing about the Riemann Zeta function if you think about it, right? So there is nothing unexpected. So how can we derive a result such that we can make the following, let's say, consideration? So we let capital N go to infinity here, summation over n, and if you remember from physics, sometimes we make the following association. We associate the following summation to minus 1 over 12. But how can we do something like this? Well, the considerations that we have done so far are very useful now, but we have to do something different. In particular, we will let, of course, n go to infinity. But remember that we also have something else. We have alpha go to 0, so we have the following limit to take. And we will assume that n will go to infinity faster than alpha goes to 0, than how alpha goes to 0. So in particular, we will assume that n alpha will go to infinity. So alpha will still go to 0, n will still go to infinity, but we will assume that n alpha goes to infinity. Why is this useful? Well, because remember our formulas. So we started from here to derive this result. Remember that we derived this result, and this was our starting point. But now if n alpha goes to infinity, we can neglect this term in the summation. So in particular, in this case, if we go below, and if we want to calculate something like this, we have to neglect this term. So we can neglect this term. Let me do it here on the side. In particular, we want to calculate the following summation over n from 1 to capital N. Remember that we will let capital N go to infinity, and remember the assumptions that we have just done. We have n e to the minus n alpha. So now, we have to remember that we have to let alpha go to 0, 0 plus. And this will be equal to, So remember also that we have a derivative with respect to alpha, and at the end of the day we will have to let alpha go to 0, 0 plus. In this case, instead of replacing this expression, and also remember that, I mean, we can neglect this minus 1 because when we take the derivative, this will give us no contribution. But we can also set this exponential here to 0 because we assumed that alpha n will go to infinity. So this exponential will go to 0. So in particular, this expression will simplify because this first part is equal to 1. So we have 1 over alpha, 1 over alpha, and then of course we are left with all these terms. We are left with all these terms here. So let me rewrite that. 1 plus alpha over 2 factorial minus alpha squared over 3 factorial plus dot 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 plus alpha over 2 factorial minus alpha squared over 3 factorial plus dot 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 squared plus dot dot dot, and we have something like this. Now, this is quite interesting because when we consider the only contributions, because remember that we have to set alpha alpha will have to go to 0. So this first term will give us a divergence, in particular 1 over alpha. So let me rewrite it like this, minus derivative with respect to alpha. Then we have 1 over alpha. Then we have plus 1 over 2 factorial, which is 1 over 2, from here and here. Then we have minus alpha over 3 factorial. And then if we consider these terms in here, remember that this will give a higher order terms because, for example, here we have a term proportional to alpha cubed. When we divide by alpha, we have a term proportional to alpha squared. So when we take the derivative, we have a term proportional to alpha. And when we let alpha go to 0, that will give us no contribution, right? So we can neglect these terms. But there is one more term that we have to consider from here, right? When we square this first term, we have plus alpha squared divided by 4, and we have to divide it by alpha. So this alpha squared will become alpha. And if you check, if you think about it, these other terms will go to 0. Will go to 0 when we take the limit alpha, when we take the derivative and when we let alpha go to 0 plus. So they are negligible in our considerations. So if we rewrite this, we have minus derivative with respect to alpha of 1 over alpha. And then, of course, this is just a constant. And here, when you consider these two terms, you have plus 1 over 3 factorial, which is 1 over 6, minus 1 over 4. So you have 1 over 6 minus 1 over 4. And what is this? Well, you can rewrite this as 2 over 12 minus 3 over 12. So this is minus 1 over 12, right? And this is exactly zeta calculated at minus 1. So this is the Riemann Zeta function evaluated at zeta equal to minus 1. And this is something actually very, very general because if you do very similar considerations to what we have done so far, you can also write a more generic formula like this. So you have a summation over n from 1 to capital N, which goes to infinity. Remember that you have to let alpha go to 0 plus. Here you have n to the power k, and then you have e to the minus n alpha. This is equal to zeta evaluated at minus k, and then you have plus minus 1 to the power k, and then here you have derivatives of order k of this divergent term 1 over alpha. Remember that alpha has to go to 0, so you have to take in principle these derivatives, and then you will let alpha go to 0, right? So it's a generalization of what we did in here. It is possible to do the calculation for other values of k, And in that case, you have to be a little bit more careful because there are higher order terms that you have to consider in the summation, and this will give rise to zeta of minus k. So this is something actually quite interesting because at this point you can see the association between summations. So when you let alpha go to 0, you have to think that this summation here will come closer and closer to the following summation. In this case, you have n to the power k, because this exponential will be close to 1 when we have, alpha goes to 0. So even for large values of n, this will be still equal to, approximately equal to 1, right? But remember that in the limit, we have supposed that n alpha will go to infinity. So at some point, you have some kind of cutoff. So the cutoff means that this exponential will decay, and therefore this summation will also be truncated, which is something that, if you think about it, is something physical. Because, I mean, also in quantum field theory and in other theories of physics like string theory, you have, if you construct the theory, you have summations of this kind. But it makes sense to think, for example, in the Casimir effect, that at some point it is not possible to consider the summation. So you have to truncate it because you don't know what's going to happen to the theory. The theory might should break down after you reach a certain point, because the higher frequencies, remember that in general these summations here are performed on some frequencies. So you can think of these as some frequencies, and when you exceed some frequencies, which is, something related to n, so if you exceed some frequency, you will, in principle, have to truncate the summation. This is the physical intuition. I know that it is not rigorous, and not everybody might be satisfied, especially those who want to be mathematically rigorous, because at the end of the day, this is not something precise. It is based upon some intuition that is not acceptable to rigorous mathematicians, and I'm aware of that. So this is not the point. The point is not to be rigorous, but it is to show more intuitively than I have seen online in general, the association between the zeta function and this type of summation here. It is also possible to do it more rigorously. For example, in a course on complex calculus, I have shown how to extend the definition of the Riemann Zeta function for negative values. So remember that in general, for when you have the real part of s greater than 1, the Riemann Zeta function can be defined like this, a summation like this, where n goes from 1 to infinity. So this is actually zeta of s, and in principle it is possible to extend this definition also for values that do not comply with this condition here. So you can, for example, define z of minus 2 and minus 3 and so on. Also negative real numbers. You can define it for negative real numbers, but it is not what I want to do in this video. I wanted to show how you can extend the reasoning when you have this type of summations here, and associate them with the Riemann zeta function. So let me do something more. In particular, I want to show you that you can interpret this formula also for negative values of k. So you might wonder, wow, it's impossible to extend this formula to negative integers, because here you have a derivative with respect to that integer. So how do you think, for example, of the derivative with respect to, the -1th derivative with respect to alpha? Well, you can think of this as the integral with respect to alpha. So this is the inverse of with respect to the derivative, and you can think of this as an integral. So, for example, d minus 2, d alpha minus 2, this would be like a double integral. So you have to integrate twice with respect to alpha. And you have to think that, so remember that when you integrate with respect to a variable, you might add an additive constant, right? So when you perform the integral x dx, so the indefinite integral, you have x squared over 2 plus a constant in general. In this case, when we consider this kind of definition here, you will not have to include this constant. I want to show you just a couple of examples. So, for example, let's calculate the following summation from 1 to n going to infinity, e to the minus n alpha divided by n squared. Remember that we have to let alpha go to 0, so I'm not going to write it every time because otherwise it would clutter my notation too much. But remember that alpha goes to 0, so in principle this is like the following series, summation 1 over n squared, n from 1 to infinity. Okay, so if we use that formula, you have z of 2, because we set k equal to minus 2, so here you have z of 2, and then you have plus, then here this derivative will become a double integral. So you integrate one time 1 over alpha, and then you integrate it another time. So actually, when you integrate 1 over alpha, you get natural log of alpha. So you have to integrate it one more time, and this will become alpha ln alpha minus alpha. So it's easy to integrate it by parts, and this is what you get. But now when you let alpha go to 0, this alpha here will go to 0, and if you think about it, alpha multiplied by ln alpha will also go to 0. So if you calculate it with the limit, this will give you 0, right? The logarithm of a quantity which goes to 0 will give rise to minus infinity. So this is actually an indeterminate form, but it can be done. So you can write it as ln alpha divided by 1 over alpha, for example, like this. And then remember that alpha goes to 0. So when alpha goes to 0, this will give rise to infinity, and this will give you an infinity. So you can use the L'Hopital. So you can take the derivative of the numerator, which is 1 over alpha, and the derivative of the denominator, which is minus 1 over alpha squared. So this is equal to minus alpha, and when alpha goes to 0, this will go to 0. Simple as that. And therefore, here you find out that z of 2 is actually defined as n from 1 to infinity 1 over n squared. So it's something that is not rigorous, because remember that here we have assumed that these quantities at some point will go to 0, so they will be truncated. Think about it, they will be truncated because we assume that capital N times alpha goes to infinity. So there is some value for n such that this exponential will go to 0. So it is not exactly coincident with this summation here, but it makes much more sense with respect to summations of the following kind. For example, n squared e to the minus n alpha, because when this goes to 0, this is actually large. But in this case, when this goes to 0, this also, remember here we have 1 over n squared, and that also goes to 0. So it is actually quite different when here we have n squared in the denominator. But as I said, this is just intuition. But let me do some more examples here, because this is actually interesting. For example, let's consider the summation over n from 1 to infinity. And remember that this is n going to infinity, capital N going to infinity. Here we have e to the minus n alpha divided by n. So here we have z of 1 plus 1. And then if you put inside this formula k equal to minus 1, you have minus, and then you have the integral 1 over alpha d alpha. So this will give you log alpha, natural log alpha. Remember that alpha will go to 0, but Now, at this point, I want you to remember another formula that I have derived on other occasions, but in this case, I don't have time to discuss. So now this is approximately the summation from 1 to infinity of 1 over n. And this summation can also be written as gamma, which is a constant. In particular, this is the Euler-Mascheroni constant, plus natural log of capital N. So this is actually capital N here. And this is, so you have to think that this is an infinity, because the Euler-Mascheroni constant is defined as the difference between this summation and an integral of 1 over x dx from 1 to infinity. So remember that this infinity actually is n, so we let n go to infinity. So this is also how we can rewrite this series here, right? So we have a divergence on the left, gamma plus ln n, z of 1, and then here we have minus ln alpha. But now, take a look. Here we have z of 1 equal to a constant gamma plus ln. If we put this on the left, we can also rewrite this as n alpha here inside the argument of ln. But now remember that when both n and alpha go to, alpha goes to 0, n goes to infinity, but remember that we assume that n alpha goes to infinity in our considerations. Therefore, this will give rise to an infinity. Now, if you go and check the value that the zeta function has for its argument equal to 1, you see a divergence. So this is an intuitive way to explain why there is a divergence at z of 1, right? Let me finish my considerations with these other examples. So we have summation over n from 1 to infinity, e to the minus n alpha over n cubed, and this is equal to z of 3. And now remember that you have to integrate 3 times 1 over alpha. So when you integrate it twice, you have alpha ln alpha minus alpha. So you have to integrate it one more time. And here you have a minus, because remember that you have minus 1 to the power 3. So here you will have a minus. But now when you integrate this function, you have something like alpha squared over 4 2 ln alpha minus 3. So this will give rise to 0 when alpha goes to 0. And when alpha goes to 0, here you will have something which is very, very close to 1 for many values, because remember that alpha goes to 0, so it's a very small quantity. At some point, this summation will truncate. So it's true that it will truncate because this exponential will go to 0 and it will not go to 1. But this can be intuitively represented as the following summation here. And what you get is that this is equal to zeta 3, like this.